Hi, welcome back to Easy Math by Dr. Nasir, your path to math confidence. Don't forget to share, like, and subscribe so you never miss a conceptual concrete lesson. Well, in today's lecture, we will see some exercises related to first order linear ODEs. Well, see an exercise. Find the general solution of the ODE y dx is equal to y into exponential of y minus 2x into dy, where y belongs to r other than 0. Determine whether there is any transient term in the general solution. Well, see solution. The given ODE 1.1 can be expressed as ds by dy is equal to y exponential of y minus 2x over y, where y belongs to r other than 0. So we have ds by dy plus 2 over y into x is equal to exponential of y, where y belongs to r other than 0, which is a first order linear ODE independent variable x. Comparing the ODE 1.2 with standard form, we have p of y is equal to 2 over y, where y belongs to r rather than 0. So integrating factor is mu of y is equal to exponential of integral of p of y dy, which is equal to exponential of integral of 2 over y dy. So we have exponential 2 log of y absolute, which is equal to exponential of log of y absolute square, which is equal to y absolute square. So mu of y is equal to y square, where y belongs to r rather than 0. Multiplying the ODE 1/2 by the integrating factor, we have y square ds by dy plus 2yx is equal to y square into exponential of y, where y belongs to r rather than 0. Well, this can be expressed as d by dy of xy square is equal to y square exponential of y, where y belongs to r rather than 0. So we have d of xy square is equal to y square exponential of y dy, where y belongs to r rather than 0. Taking integral, we have integral of d of xy square is equal to integral of y square exponential y dy plus c, where y belongs to r other than 0 and c is the arbitrary constant. So xy square is equal to y square exponential y minus integral of 2y exponential y dy plus c, where y belongs to r other than 0 and c is the arbitrary constant. So we have y square exponential y minus 2 integral of y exponential y dy plus c, where y belongs to r other than 0 and c is the arbitrary constant. Now we evaluate this integral, we integrate this by parts. So xy square is equal to y square exponential of y minus 2y exponential y plus 2 integral of exponential y dy plus c, where y belongs to r other than 0 and c is the arbitrary constant. So xy square is equal to y square exponential y minus 2y exponential y plus 2 exponential y plus c, where y belongs to r other than 0 and c is the arbitrary constant. So xy square is equal to y square minus 2y plus 2 into exponential y plus c, where y belongs to r other than 0 and c is the arbitrary constant. Now dividing this by y square, we have x of y is equal to 1 minus 2 over y plus 2 over y square into exponential y plus c over y square, where y belongs to r other than 0 and c is the arbitrary constant, which is the required general solution and contains the transient term 1 over y square. Well, see another exercise. Find the general solution of the ODE cosine x dy by dx plus sin x into y is equal to 1, where x belongs to omega and omega is equal to r other than plus minus 2 and minus 1 pi by 2, where n belongs to n. Determine whether there is any transient term in the general solution. Well, see solution. The given ODE 1.3 can be expressed as dy by dx plus tangent x into y is equal to secant x, where x belongs to omega. Comparing the ODE 1.4 with the standard form, we have p of x is equal to tangent x, where x belongs to omega. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of tangent x dx. So we have exponential minus log of cosine x absolute, which is equal to exponential of log of cosine x absolute exponent minus 1, which is equal to 1 of cosine x absolute. So mu of x is equal to secant x absolute, where x belongs to omega. Multiplying ODE 1.4 by the integrating factor, we have secant x absolute dy by dx plus secant x absolute into tangent x into y is equal to secant x absolute into secant x where epsilon to omega. Now for epsilon to omega plus, which is defined as union or k belong to z of open interval minus pi by 2 plus 2k pi, pi by 2 plus 2k pi, secant x absolute is equal to secant x. Therefore, from 1.5 we have secant x into dy by dx plus secant x into tangent x into y is equal to secant x into secant x where epsilon to omega plus. So we have secant x into dy by dx plus secant x into tangent x into y is equal to secant square x where epsilon to omega plus. Well, this can be expressed as d by dx of secant x into y is equal to secant square x where epsilon to omega plus. So we have d of secant x into y is equal to secant square x dx where epsilon to omega plus. Taking integral, we have integral of d of secant x into y is equal to integral of secant square x dx plus c, where epsilon to omega plus and c is arbitrary constant. So we have secant x into y is equal to tangent x plus c, where epsilon to omega plus and c is arbitrary constant. Now dividing this by secant x, we have y of x is equal to tangent x plus c over secant x, where epsilon to omega plus and c is arbitrary constant. Now for epsilon to omega minus, which is defined as omega other than omega plus, secant x absolute is equal to minus secant x. Therefore, from equation 1.5 we have minus secant x into dy by dx plus minus secant x into tangent x into y is equal to minus secant x into secant x, where epsilon to omega minus. So we have secant x into dy by dx plus secant x into tangent x into y is equal to secant x into secant x, where epsilon to omega minus. So secant x into dy by dx plus secant x into tangent x into y is equal to secant square x, where epsilon to omega minus. Well, this can be expressed as d by dx of secant x into y is equal to secant square x, where epsilon to omega minus. So we have d of secant x into y is equal to secant square x dx, where epsilon to omega minus. Now taking integral, we have integral of d of secant x into y is equal to integral of secant square x dx plus c, where epsilon to omega minus and c is arbitrary constant. So we have secant x into y is equal to tangent x plus c, where epsilon to omega minus and c is arbitrary constant. Now dividing this by secant x, we have y of x is equal to tangent x plus c over secant x, where epsilon to omega minus and c is arbitrary constant. Thus from equations 1.6 and 1.7 we have y of x equal to tangent x plus c over secant x, where epsilon to omega and c is arbitrary constant, which is a required general solution and does not contain any transition term. Well, see another exercise. Find the general solution of the ODE cosine square x into sin x into dy by dx plus cosine cube x into y is equal to 1, where epsilon to omega, which is defined as r other than k pi by 2, where k belongs to z. Determine whether there is any transition term in the general solution. Well, see solution. The given ODE 1.8 can be expressed as dy by dx plus cosine cube x over cosine square x into sin x into y is equal to 1 of cosine square x into sin x, where epsilon to omega. So we have dy by dx plus cotangent x into y is equal to 1 of cosine square x into sin x, where epsilon to omega. Comparing the ODE 1.9 with standard form, we have p of x is equal to cotangent x, where epsilon to omega. So integrating factor is mu of x is equal to exponential of integral of p s dx, which is equal to exponential of integral of cotangent x dx, which is equal to exponential log of sin x absolute. So mu of x is equal to sin x absolute, where epsilon to omega. Multiplying the ODE 1.9 by the integrating factor, we have sin x absolute dy by dx plus sin x absolute into cotangent x into y is equal to sin x absolute over cosine square x into sin x, where epsilon to omega. Now for epsilon to omega plus, which is defined as union over k belong to z of 2k pi up to 2k plus 1 pi open interval intersection with omega, sin x absolute is equal to sin x. Therefore from 1/10 we have sin x into dy by dx plus sin x into cotangent x y is equal to sin x over cosine square x into sin x, with epsilon to omega plus. So we have sin x into dy by dx plus cosine x into y is equal to 1 over cosine square x, with epsilon to omega plus. Well, this can be expressed as d by dx of sin x into y is equal to secant square x where epsilon to omega plus. So d of sine x into y is equal to secant square s dx, where epsilon to omega plus. Now taking integral, we have integral of d of sine x into y is equal to integral of secant square x dx plus c, where epsilon to omega plus and c is arbitrary constant. So sine x into y is equal to tangent x plus c, where epsilon to omega plus and c is arbitrary constant. Now dividing this by sine x, we have y of x is equal to tangent x plus c over sine x, where epsilon to omega plus and c is arbitrary constant. Now for epsilon to omega minus, which is defined as omega other than omega plus, sine x absolute is equal to minus sine x. Therefore from 1.10 we have minus sine x divided by dx minus sine x into cotangent x into y is equal to minus sine x of cosine square x into sine x, where epsilon to omega minus. So sine x into dy by dx plus sine x into cotangent x into y is equal to sine x over cosine square x into sine x, where epsilon to omega minus. So sine x dy by dx plus cosine x into y is equal to 1 over cosine square x, where epsilon to omega minus. Well, this can be expressed as d by dx of sine x into y is equal to secant square x, where epsilon to omega minus. So d of sine x into y is equal to secant square x dx, where epsilon to omega minus. Now taking integral, we have integral of d of sine x into y is equal to integral of secant square x dx plus c, where epsilon to omega minus and c is arbitrary constant. So sine x into y is equal to tangent x plus c, where epsilon to omega minus and c is arbitrary constant. Now dividing this by sine x, we have y of x is equal to tangent x plus c over sine x, where epsilon to omega minus and c is arbitrary constant. Thus from equations 1.11 and 1.12 we have y of x is equal to tangent x plus c over sine x, where epsilon to omega and c is arbitrary constant, which is the required general solution and it doesn't contain any transient term. We'll see another exercise. Find the general solution of the ODE s plus 1 divided by dx plus s plus 2 into y is equal to 2x exponential minus x, where epsilon to r other than minus 1. Determine whether there is any transient term in the general solution. We'll see solution. The given ODE 1.13 can be expressed as dy by dx plus s plus 2 over s plus 1 into y is equal to 2 into x over s plus 1 into exponential of minus x, where epsilon to r other than minus 1. Comparing the ODE 1.14 with standard form, we have p of x is equal to s plus 2 over s plus 1, where epsilon to r other than minus 1. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of s plus 2 over s plus 1 dx, which is equal to exponential of integral of 1 plus 1 over x plus 1 dx, which is equal to exponential of x plus log of x plus 1 absolute. So mu of x is equal to s plus 1 absolute into exponential of x, where epsilon to r other than minus 1. Multiplying equation 1.14 by the integrating factor, we have s plus 1 absolute into exponential s divided by dx plus s plus 1 absolute into s plus 2 over s plus 1 into exponential s y is equal to 2x into s plus 1 absolute over s plus 1, where epsilon to r other than minus 1. Now for epsilon to minus infinity to minus 1 open double, s plus 1 absolute is equal to minus into s plus 1. Therefore from equation 1.15 we have minus into s plus 1 exponential s divided by dx minus s plus 1 into s plus 2 over s plus 1 into exponential s into y is equal to minus 2x into s plus 1 over s plus 1, where epsilon to minus infinity to minus 1 open double. So minus into s plus 1 into exponential s divided by dx minus s plus 2 into exponential s into y is equal to minus 2x, where epsilon to minus infinity to minus 1 open double. So s plus 1 into exponential s divided by dx plus s plus 2 into exponential s y is equal to 2x, where epsilon to minus infinity to minus 1 open double. Well, this can be expressed as d by dx of s plus 1 into exponential s y is equal to 2x, where epsilon to minus infinity to minus 1 open double. So we have d of s plus 1 into exponential s y is equal to 2x dx, where epsilon to minus infinity to minus 1 open double. Now taking integral, we have integral of d of s plus 1 into exponential s y is equal to 2 into integral of s dx plus c, where epsilon to minus infinity to minus 1 open double and c is arbitrary constant. So we have s plus 1 into exponential s y is equal to sk plus c, where s belongs to minus infinity to minus 1 open interval and c is arbitrary constant. Now dividing this by s plus 1 into exponential s, we have y of x is equal to sk plus c over s plus 1 into exponential x, where s belongs to minus infinity to minus 1 open interval and c is arbitrary constant. Now for s belongs to minus 1 to plus infinity open interval, we have s plus 1 absolute is equal to s plus 1. Therefore, from equation 1.15, we have s plus 1 into exponential s dy by dx plus s plus 1 into s plus 2 over s plus 1 exponential s y is equal to 2x into s plus 1 over s plus 1, where s belongs to minus 1 to plus infinity open interval. So s plus 1 into exponential s dy by dx plus s plus 2 into exponential s y is equal to 2x, where s belongs to minus 1 to plus infinity open interval. Well, this can be expressed as d by dx of s plus 1 into exponential s y is equal to 2x, where s belongs to minus 1 to plus infinity open interval. So d of s plus 1 exponential s y is equal to 2x dx, where s belongs to minus 1 to plus infinity open interval. Now taking integral, we have integral of d of s plus 1 exponential s y is equal to 2 into integral of s ds plus c, where s belongs to minus 1 to plus infinity open interval and c is arbitrary constant. So we have s plus 1 into exponential s y is equal to sk plus c, where s belongs to minus 1 to plus infinity open intervals and c is arbitrary constant. Now dividing this by s plus 1, we have y of x is equal to sk plus c over s plus 1 into exponential x, where s belongs to minus 1 to plus infinity open interval and c is arbitrary constant. Now from equations 1.16 and 1.17, we have y of x is equal to sk plus c over s plus 1 into exponential x, where s belongs to r other than minus 1 and c is arbitrary constant, which is the required general solution and contains triangular term exponential minus x over s plus 1. We'll see another exercise. Find the general solution of the ODE s plus 2 square dy by dx is equal to 5 minus 8y minus 4xy, where s belongs to r other than minus 2. Determine whether there is triangular term in the general solution. We'll see solution. The given ODE 1.18 can be expressed as s plus 2 square dy by dx plus 4 into s plus 2 into y is equal to 5, where s belongs to r other than minus 2. Well, this can be expressed as dy by dx plus 4 over s plus 2 into y is equal to 5 over s plus 2 square, where s belongs to r other than minus 2. Comparing the ODE 1.19 with standard form, we have px is equal to 4 over s plus 2, where s belongs to r other than minus 2. So integrating factor is mu x is equal to exponential of integral of px dx, which is equal to exponential of integral of 4 over s plus 2 dx, which is equal to exponential 4 log of s plus 2 absolute, which is equal to exponential log of s plus 2 absolute exponent 4, which is equal to exponential log of s plus 2 absolute exponent 4, which is equal to s plus 2 absolute exponent 4. So mu x is equal to s plus 2 exponent 4, where s belongs to r other than minus 2. Multiplying the OD 1.19 by integrating factor, we have s plus 2 exponent 4 dy by dx plus 4 into s plus 2 cubed into y is equal to 5 into s plus 2 square, where s belongs to r other than minus 2. Well, this can be expressed as d by dx of s plus 2 exponent 4 into y is equal to 5 into s plus 2 square, where s belongs to r other than minus 2. So d of s plus 2 exponent 4 into y is equal to 5 into s plus 2 square dx, where s belongs to r other than minus 2. Now taking integral, we have integral of d of s plus 2 exponent 4 into y is equal to integral of 5 into s plus 2 square ds plus c, where s belongs to r other than minus 2 and c is arbitrary constant. So s plus 2 exponent 4 into y is equal to 5 by 3 into s plus 2 cube plus c, where s belongs to r other than minus 2 and c is arbitrary constant. While dividing this equation by s plus 2 exponent 4, we have y of x equal to 5 by 3 into s plus 2 plus c over s plus 2 exponent 4, where s belongs to r other than minus 2 and c is arbitrary constant, which is the required general solution and contains triangular terms 5 over 3 into s plus 2 and 1 over s plus 2 exponent 4. That's it for today. Well, in next lecture we will see some more exercises related to first order linear ODEs. Don't forget to share, like and subscribe Easy Math with Dr. Nasir, so you never miss a conceptual concrete lesson.